Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. Well, Andrew, it's a pleasure to be here. You've always been a great supporter of formal methods and sort of trustworthy computing work at MSRC, so it's a delight to be able to give you a progress report on what we've been doing. So this is joint work with a couple of students that we've worked with at the Open University, Misha Isatulin and Francois Dupressoir, my colleague Jan Jurjens at Dortmund, who is a Royal Society Research Fellow here, more on that later, and Dave Nauman, who is a visitor from Stevens. So, I mean, this is a general talk about software verification, and in particular looking at C. And you know, to get some sort of traction, you need to specialize. So we have had a long-term interest in this lab on cryptographic protocols. Initially, we looked at them in a very abstract setting of process calculi of the pi calculus. But this talk is about looking actually at implementation code of crypto protocols and seeking to show not just that they're memory safe, but that they enjoy security properties like keeping keys secret, keeping confidential information secret, authenticating others, and so forth. So in my talk, what I want to do is to speak about where we are, the state of the art, and say a bit about what's next. And I'm going to use a particular example protocol as a running example, and take you through where we were. So I'll start with some background. And it's a kind of, I'm not sure how this compares to your own personal journey, but for me, it's been a little bit bizarre. And I joined this company, and I was working on this sort of very abstract process calculi. And then after a while, we moved down to writing protocols in F#. And then most recently, we're going down to C. So maybe it's going to be assembler next. I don't know. So just a general motivation, these kinds of protocols are hard to get right. That was true when they were being developed in the academic literature. So there was a famous protocol by Needham and Schroeder from '77, which turned out, or there were two protocols in their paper, and one of them had a bug that was discovered a few years later, and the other one had a bug that was discovered I think 17 years later. And then 4 years after that, the IETF standardized it with the bug, which caused one of these recalls. I think this one up here. So these things are hard to get right. They're hard to get right in the academic literature. Moreover, where you know, as cryptographic software has become prevalent with the internet, we're finding that implementation code is going wrong as well. Our response to this is, well, you know, you could try and get the design right, which you certainly try and do, but even better if you can actually prove something about the bits themselves. And with a lot of progress in the last 10 years on being able to verify low-level implementation code, we figured maybe we can teach those low-level tools to actually prove security properties about the implementation code. So what we did, so we started working on implementations in about 2005, and then after a few years, we got to this point. So this is kind of a busy slide. This is the poster, in fact, for a presentation we had at the joint center with INRIA over in Paris, the MSR INRIA center. And we've had a long-standing successful collaboration with them. My colleague Cedric Fournet, who I don't think is here, and I from Cambridge have collaborated with folks over there. And so a few years ago, after some years' effort, we'd got this nice cryptographic verification kit. And the idea was that you write reference implementations of your crypto protocol in a high-level language F#, and then we got a variety of backends that we could use to verify properties of the code. So the idea is you have your code here, and then you can actually run it using the ordinary F# compiler, but then there are various other tools that could prove security properties of the F# code. And we were very proud. We had some big case studies of, you know, 2,000, 3,000 lines of code, things like WS security, and TLS, and a number of other protocols. So we're very proud. And then our bubble was burst. We had some people here from GCHU came along to hear what MSI was doing on security. And they said, Andy, it's all very well, but no one writes these protocols in F#, not even ML. So everyone does it in C. So we were kind of a bit, sugar, what are we going to do? All right, well, let's take the feedback to heart, and let's try and see if we can port our techniques to work with C. So I was asked to sit on a panel around about the time this happened, and put this up, speaking about the rise of code verification. This is the panel at the Computer Security Foundation Symposium, which is one of the main IEEE conferences in this area. And I was predicting that, you know, we'd spent 20 years using process calculus and other things to try and write models of protocols and verify them. But what I was predicting was the next 20 years about verifying code. You know, things have moved on. We can, you know, reason about F# programs, ML programs. We can reason, in fact, possibly even about C programs. And I argued that if we could verify code in the languages people actually used, we could find and fix the security properties as they're actually implemented, and get away from this business about there being bugs in the spec, or maybe the spec is correct and the implementation is wrong. I mean, the first time most protocols are actually properly formalized is in code. So let's see if we can analyze the code. So I blogged about this, and my colleague Jan Jurens got in touch, and he said, maybe I can come visit and become a Royal Society Industry Fellow here. And I said, sure. So I mailed Andrew and said, maybe we can, you know, support this and write to the Royal Society. And I think you have to actually produce a letter in support of Jan. And I volunteered, maybe I'll ghostwrite it for you, so you don't have to go through all the trouble. So I started to write it here. And so Andrew replied. I couldn't have put it better myself. So I felt very proud at this ghostwriting malarkey, and I thought, well, maybe the next time what I'll do is maybe I can ghostwrite my performance review. But Andrew declined for some reason. So anyway, okay, that's a bit of background. So let's look at some code and look at a protocol. So this is a simple protocol. This is actually running. And what it's doing is there's two parties. They each share a long-term, or they share a symmetric key, and we want to secure a request response. So the request is going to be encrypted with the key, and the request is going to include a session key that's used to encrypt the response. And so you get freshness of the response because it was a fresh session key. And so if you run it, you get something like this. If you actually write it on the whiteboard, and this is much more readable, you would write this sort of thing. So A sends to B his identity together with the request encrypted under their shared key and the session key, and then B sends back the response encrypted under the session key. So these are the kind of descriptions you write on the whiteboard, but it's hard to analyze these directly. So what's next is roughly where we were about 5 years ago, that we can write this in process calculus. So to describe this protocol, we would write this sort of stuff in process calculus. And this is the notation of a tool called ProVerif that can automatically analyze PyCalculus models. So we have some stuff up here that declares a channel C. Here we've got authenticated encryption. So you have an equation. So E is encrypting X with a key K. And then D is decryption. And this equation is saying that if you try and decrypt this ciphertext with K, you get back to the plain text. And then, whoopsie-daisy, you need other. And we needed this stuff to represent the pairing that's going on in these, the concatenation that's going on in these messages. So we have a concatenation operator with some destructors. So with a bit of work, you can write this sort of thing. So you can write a bit of code that represents the behavior of A, and a bit of code that represents the behavior of B. And you can see the sort of thing it goes through. That I won't go into all the detail, but you can see it forms encryptions. And then here's B receiving some messages. And he does some decryptions to get that, or to check the message and get its contents. And we also embed some events in the protocol to represent progress through the thing. So for example, you have a client begin that starts before A sends a message, and then down here you have an event server reply that indicates that he is happy to proceed, and eventually you've got a client accept. So if you run this through ProVerif, like we wait a moment, ProVerif runs on the PyCalculus model. We look at the results, and you've seen that and it's proved that if a service reply happens, then a client begin had happened, and it proves that if a client accept happens, then the server had replied, and with the same parameters. And we also have this check up here to make sure you can actually reach the end. So a classic error in these kind of models is you write something that doesn't actually do anything. So you're checking that it does actually get to the end. So that's roughly where we were. So we want to automate this. So I worked with a couple of PhD students on this. And one of them is Misha Izatulin, and this is his work. And we're publishing this at ACM CCS in a couple of weeks. So this is an approach based on symbolic execution. And I didn't think Misha could pull this one off, I have to say. But I'm very impressed with what he's been able to do. So the first assumption here is that crypto protocols are a special kind of protocol where, I mean, they're generally written on top of some sort of transport that gives you some reliability, and they're they pretty much should drop dead or go back to the start if any error occurs. So the idea of this is that to get a model of the protocol, we just run it on concrete test data, just compile and run it. But we modify the compilation so we keep track of the instructions that are executed, that you pass through it. And then in the second pass, we can run this trace of the concrete execution against the symbolic representation of the heap to get a symbolic representation of all the computations, and then we can turn that into pi calculus. So I can reveal that if you thought the ProVerif code I showed you earlier had a slightly kind of maybe machine look to it, I can reveal it was actually automatically generated. So it's very much the kind of thing you'd write, but by using this technique, we can actually automatically generate this model. So this is just going through the different steps that we run it and we get this log of the concrete executions, and then we have a second symbolic execution of driven by that trace. And after that, we can generate pi calculus model or process calculus model, but it still has a lot of bit manipulating operations. So at this point, we can do a lot of rewrites to simplify the manipulation of bits to get back down to the term algebra that we were using. And so you get back to what I showed you earlier, and then we can run ProVerif on this. So, I mean, essentially, it's a way to allow an engineer to write the protocol in C and actually do interop testing with it, but at the same time, automatically generate a pi calculus model suitable for verification. So Andrew showed us some machine code earlier. So this is kind of my equivalent. I'm not going to go through all of this, but I just want to show you that, I mean, this is an image from our paper, that you've got your C code here that's doing pointed arithmetic and what have you, copying stuff around, doing some encryption here, I think. And then what this is showing here is our symbolic representation of the heap. And we just sort of run through it symbolically, maintaining maintaining the heap. Oh, and anytime we have to instrument the runtimes to track any calls to actually cryptography. So we're not trying to verify that the actual implementation of the crypto is correct. It's more like the protocols on top of that. So we abstract away from the results of calls to crypto. And whoopsie-daisy, and get this sort of thing. And down here, when we actually are starting to do outputs on the wire, at that point, we generate this process calculus notation that represents sort of process calculus messages on the wire. So here, it's sending some lengths, and then here it's sending, oh yeah, this actual ciphertext. So this is one of the messages being actually sent. Okay, so here is just some summary information. We've got some modest programs here that we've been able to verify, and in some cases find some flaws. We found a flaw. So CISO was the pioneering paper in this area that was published about 5 years ago, and they were able to verify 1/2 of the Needham-Schroeder-Low protocol. And we actually discovered there was a memory safety error in their code that they'd been able to verify. So we were able to go a bit beyond them and spot that. And then there's been a recent project here at MSR Cambridge on smart metering led by George Donesis. And so he's using zero-knowledge proofs to communicate or to have a smart meter communicate the bill associated, with a particular household to the electricity supplier without communicating exactly when and how much electricity was used, which is, if you were to do that, you're opening up a privacy can of worms. So his code was avoiding that by using a zero-knowledge proof. So he was very keen that we try our tools on that. So we did the symbolic verification and discovered a nice bug, as it were, where it's a classic sort of C error where he's got a pointer, which is a char star that's pointing to 4 bytes. And he dereferences it here, star session key, and then extends it to 4 bytes when instead he should have been pulling all 4 bytes out. So his testing didn't discover this, of course, because the same code was being used, on both sides of the communication, but the symbolic execution did discover it. Okay, so that was one project, model extraction. It assumes the protocol follows a single collect run, and deviations should terminate immediately. And so it allows basically the engineer to write process calculus in C. And it's a bit of a heuristic, which I guess Andrew was speaking about that earlier. And ultimately we show the model is correct, but not necessarily the code, because it might have other execution behavior. So we got some ideas about maybe finding ways to backpatch the code to make sure it really does drop dead if it encounters any error. Okay, so then let me talk a bit about the second approach, which we have also published this year. And here, this is a much more, in a sense, more conventional bit of sort of program verification using a sort of a Hoare logic implemented in a tool called VCC that's out of MSR Redmond and the MSR's EMIC lab. And VCC allows us to annotate a program with assertions and also other annotations to guide the verifier, and then verify both memory safety and higher level assertions about the code. So in this case, I won't actually show you in full detail, but we have events, but we also have assertions. So here you have an event before the message is sent, and then after the message is received, we assert that that event must have occurred, or it could be that the key has become compromised. So it's important to model those kind of possibilities, and we do. So here in brief is what we do. That we previously had a a technique based on refinement types for reasoning about F-sharp programs, and refinement types are implemented in a type checker called F7. And our initial strategy was, well, let's just take this. It works fine for F-sharp. Let's recast it in the setting of C. We knew we were going to have to do a bit more work to handle memory safety, but otherwise it's still, verifying the same properties of the F-sharp code. So we took that's the theory we had developed in F7 was partly formalized in the Coq theorem prover that's been used to great effect around this lab to do various things. And we did a fairly classic definition of high and low level predicates on the symbolic terms that can arise in cryptography. And let me see, so what were the difficulties? One of the main ones was that that C, of course, manipulates very concrete byte arrays. You generally have a pointer and a length when you're dealing with byte arrays, whereas in F-sharp it's much easier. You just have an abstract type of byte arrays that you can say stuff about. So we had to, in VCC, maintain a kind of auxiliary or ghost state that associate each concrete byte array that arose during the computation with a symbolic term, a bit like the E's and the D's that I showed earlier. So we did that, and then you can get a snag where you've got two different symbolic terms, like these two, where K and K dashed and T dashed are different, where these in fact actually turn out to be equal when you look at what at runtime, which it's unlikely, of course, that's the whole point of cryptography, but it could happen. So we need to deal with that possibility, and so we kind of detect them. So we have to have some wrappers around the cryptography to detect this sort of departure from the abstraction, and there we can abort if that happens. So our verification is that the protocol is correct unless one of these unlikely collisions occur. So this is the kind of thing that we would write, where here's an API for the decryption routine, where it takes a pointer to the key together with the key length, a pointer to the ciphertext together with its length, and a pointer to the out buffer. And what it's going to do is return and it returns an error code. And then the contract says that if the error code isn't 0, then in fact the term associated with the ciphertext was in fact the encryption of the key together with the term that we produced as an output. So, I mean, there were a number of obstacles, but we were able to recast this theory that had worked for F-sharp in a much lower level, more realistic setting of C. And so here's some numbers from our paper. And so far, we've only managed this for some really quite small protocols. And one of the horrors of this is that we've got a vast number of lines of annotations. So sometimes actually, oh gosh, doubling the length of the protocol code. So this has been a bit of a heroic effort. And we're currently, as you might imagine, very fixated on figuring out how we could reduce the number of annotations that are necessary on this code base. OK, so summarizing that, I mean, using general purpose tools like VCC, and there's a number of others, does give you, it gives you a full verification. This is not a heuristic. Gives you memory safety and also security in this standard symbolic model of cryptography. Now, it doesn't prove everything, so there's a number of kind of classic cryptography attacks that we're not looking at, like power consumption, etc. So we're, let me come back to computational assumptions in a few slides' time. So Francois is now taking this further over in Redmond, looking at the next generation of the TPM. So at Build a few weeks ago, Microsoft announced that we've been working on a new version of the TPM, which will hook into Windows 8. And this will be one of the, there's a number of technological improvements over the previous version of the TPM. And I should say, a TPM is a Trusted Platform Module, which is the secure coprocessor that supports things like BitLocker on many, encrypted disks on many business laptops. So this is it's a it protects against all kinds of software vulnerabilities in the underlying operating system. And the exciting thing about the methodology that the Trusted Computing Group is using to develop this is that they're using ANSI C itself as the normative specification. So actually, TCG is actually going to standardize a C program that implements the TPM. So we're keen to apply these techniques and also the symbolic execution techniques on this code base. Okay, so Tales from the War on Error. So this is me being a little cheeky. So Sir Tony Hoare here talks about this as being the verified software initiative. I mean, I'm a mere commoner. I prefer this to think about it as we're fighting a war on error. And I have to say, we have been in the trenches. Particularly using VCC has been, a lot of effort, to be honest. Let me start at the top, though. The symbolic execution. I was surprised by that, but it's been extremely effective in being able to automatically extract verifiable models from code. Let me see. I was having a drink with Peter O'Hearn last week, and he was sort of saying that symbolic. So he's very famous for his work on separation logic, and knows a lot about the underlying technologies that are going on here, and he was kind of more or less saying, yeah, symbolic execution is one of the few things that will reliably work. So I think we're definitely going to put more attention on symbolic execution going forward. General purpose verifiers, and we thought VCC would be an easy way of transporting the F-sharp techniques. So let me see. This is kind of just looking back a little bit before I look forward. And there's three competing tools in the space. There's Framacy from INRIA and Verifast from Leuven. And we've spent time with VCC. We're also going to look at those other tools to see whether we can learn from them. But a general problem with VCC is that it's trying to prove programs are correct in a multi-threaded model. And unfortunately, so it means, unfortunately for us, that we pay a penalty of supporting multi-threaded programs when, in fact, most of our code is not multi-threaded. So it's kind of frustrating. But it's very hard to kind of modify VCC to have a laxer view of the kind of execution model. But that possibly is something we could do. Another frustration I've had is I walk around this building, and I'm in Redmond as well, and I speak to folks over there, and there's a range of tools. There's a Yogi tool over there. There's Slayer over here. A range of tools that can automatically prove memory safety of device drivers. But it just seems really hard to take the output from those tools and use them in, prove the thing's memory safe to begin with, and then take that information and then plop it into something like VCC so we could prove higher level properties. So I think that's a very interesting research question, how to combine these entirely automated tools with maybe with interactive tools. It's tempting to also build on work on entirely formalized certified semantics of C, like Xavier Leroy's CompCert project. But I think I'll probably resist that temptation, because although it would give you the confidence that the underlying framework is entirely sound, that's not really been the problem that we've experienced with this work. Our problem more has been like annotations rather than I don't think we've encountered any real soundness problems in the tools that we've been using. Another point is that we try to share these theories, and the theory we had was very much oriented towards functional programs. And in retrospect, it might have been better to have used the support for invariants that we have in VCC. And then finally, on computational models. So my colleague Cedric has made great progress since 2008 on using F7 to prove computational properties of crypto protocols. And that's within the probabilistic models that cryptographers use. And I think it would be great to leverage that now and combine the two to get computational results about C. OK, and another thing, and this is also going forward, is like we want to really take some leadership in the community and establish a challenge website. I mean, we found this pretty hard, and we've had access to kind of a whole wide range of tools and expertise within the company. So we're setting up this website called the CSEC Challenge, where we're going to curate small examples of protocols and invite people who are specialists in verification, but maybe not in security, to see if they can find bugs in them or help us to go further. And also, if we can establish sort of benchmark examples, it's going to make it easier to compare techniques as they go forward to see if they can verify more of these protocols. So I'm working with other folks from universities, the Open University, CMU, et cetera, to establish this site. And when we go live on Wednesday, we already will have about half a dozen collections there. So I hope that initiative will help the research community in this space. My final slide, we have a problem that, let's see, what have I said? We've looked at the problem of verifying cryptographic code in C. I mean, it's essential for the security of our infrastructure, and yet it has many bugs. Every few years, or in fact more than that, every year there's a few kind of significant bugs in shipped code. I mean, a change that's happening now, and I think will continue in the future, is that designers are appreciating the need for reference implementations. I was speaking to Ian Pratt earlier at lunchtime, and he was saying that they'd actually, in their company, they had been using the TPM and actually trying to do some of the things it was intended to do attestation and secure boot with it, and discovered that many of these devices just don't interoperate very well. And so we had a lot of portability problems. And I think the folks in the TCG totally agree with that. And this is a quote from a slide from last year. They said they've taken years to achieve good TPM interoperability, and maybe according to Ian, they still aren't quite there yet. So they need a precise language. When we started, we tried to persuade them to use F#, actually. So a few years ago, we had an internship where we were using F# to specify the next version of the TPM. And that was very beautiful, because you could take the F# and verify it, and you could also generate reasonably clean C. But it just didn't work in practice because of the economics of it all and the sort of social aspect of it all, that a specification needs to be read and understood and trusted by a whole many different folks in the community, like engineers, the people building the chips, and then the folks who are writing the low-level software that is interacting with it. So starting from F#, I'm afraid, doesn't really work. I mean, so people give me a hard time about that. They say, Andy, you did your PhD in functional programming. Aren't you just selling us out? And I say, no. I think F#, I mean, it's great for adventurous programmers. It's great. I mean, functional programming generally is great for startups. Functional programming gives you a competitive advantage. But if you're trying to do something like defining a standard, you're not looking for a competitive advantage. You're looking for a sort of common language. So I think at that point we need to kind of be humble and take ideas that worked in functional programming, like the use of automated solvers, and move them down to C. So I think that's the direction I would advocate. And I think we're not there yet, but I think within a few years we should be able to do things like verifying this new implementation of the TPM, and verifying other bits of crypto software like TLS and so forth. So let me just finish there. Thank you for your attention.
That's great. Thanks, Andy. Do we have any questions? Yes, we do have a question right there. You can just wait for the microphone.
So really an observation rather than a question. I mean, isn't it amazing how conservative people are in computer science? The entire subject for your talk was essentially the right tools for solving this problem exist. Real programmers won't use them, so therefore we had to work around what real programmers really do. Isn't that a sad commentary on the way this industry works?
Well, it's software economics. Yeah, I'm a little sad about it. I've kind of got over it. And well, there was Paul Graham, the venture capitalist. I mean, he gave a talk about functional programming at ICFP, and he says, you guys just don't get it. You think people at ICFP get together every year and go, oh, no one's adopting Haskell, no one's adopting ML, or whatever, though in fact Haskell's been doing great. But anyway, they lament this problem. And he said, you're looking at it from the wrong point of view. And this is coming back to, Andrew the entrepreneur. From an entrepreneurial point of view, it means you've got a competitive advantage. There's Ian Pratt. His company was based on code in OCaml. I think it's roughly fair to say. Those guys, and I think others like them, have had a big competitive advantage from using, ML and F#. And that's what we use to write our code ourselves. But if you're trying to communicate with people, something like C is very effective.